Good morning. Happy Monday. I am so groggy today. I slept really well last night, but I just feel so groggy. Wait for a couple more people. Well, maybe I'll just do a little review while we're waiting for people to join up. So last time we discussed circular motion, or we began to discuss circular motion, and so we have an object moving in a circle. The radius of that circle is r, and wherever you are in that circle, the velocity is going to be tangent to the circle, and the acceleration is going to point towards the center of the circle. Okay? I gave you some formulas for velocity, or I should say speed, in circular motion. It's 2 pi times the radius divided by the period. Okay. And then I gave you an equation for the centripetal acceleration, which is v squared over r. Okay. There was an alternative equation, which is 4 pi squared r divided by period squared. These both give the same numerical answer, just in terms of different variables. Newton's, so this was called the centripetal acceleration. Newton's second law applies equally well to circular motion as it does to linear motion. And so if you're moving in a circle, the force required to make you move in that circle is going to be mass times v squared over r, or mass times 4 pi squared r over t squared. So whatever force is causing you to go in a circle, that is called the centripetal force. Okay. And so it could be any force, really. But the centripetal force has to point towards the center of the circle at all times. Okay. Zoom one out so you can see the whole page. So that's what we learned last time. So the first thing we're going to talk about today is what's called a horizontal circle. So horizontal circles are circles that are going around like this. Okay? The next thing we're going to talk about after I'm done with this part is vertical circles, where the circle is, like a Ferris wheel. Okay? And these are two kind of different animals. Okay? If we think about a horizontal circle, if we're looking at the circle, sort of an edge-on view of the circle, if you're looking at something that's moving in a circle edge on, it's kind of going back and forth like this, okay? And if we think about it, the centripetal force is pointing horizontally, okay? Because the center of the circle is right here, so it points towards the center of the circle. And if we think about gravity, gravity is perpendicular to the circle, okay? So for horizontal circles, gravity is not a centripetal force. Okay, and so that actually kind of simplifies the problem, and we'll see why once we go to vertical circles. But so gravity is never going to be a centripetal force if we have a horizontal circle. Okay, so let's do an example. Let's suppose you have a spring of stiffness let's say a spring of stiffness 140 newtons per meter and natural length 0 meters. So this spring is like just goes, has length 0. Okay. Has a 4 kilogram mass attached to the end. Okay. It is whirled in a circle with speed it was whirled in a circle with speed 11 meters per second. What is the radius of the circle? Okay. So this is and I should have said horizontal circle. So horizontal circle. So if we think about this problem from a top-down perspective, so top view, here's the circle. And at the center of the circle, here's the center of the circle. Someone's holding one end of the spring, and then the spring is extending out to the edge of the circle, and at the edge of the circle there's a mass. Okay, so we're going to use Newton's second law. F equals ma. All right. Now the force. What is the force that is keeping the what is the force that is keeping this mass moving in a circle? Well, it's going to be the elastic force. Okay, so on the left-hand side of Newton's second law, I'm going to write kx, because that's the formula for the elastic force. On the right-hand side, see how I gave you the speed? Okay, so because I gave you the speed, we're not going to use the 4 pi squared r over t squared version of centripetal acceleration, because that doesn't have speed in it. This is the version that has speed in it. Okay, so we have, all right, so we have mv squared over r. Now we got to be a little bit careful here. So remember, x represents the extension of the spring. Okay, x represents the extension of the spring, which is not necessarily equal to the radius of the circle. Okay, so for example, what if we had this spring has a natural length of 0 meters. Okay, so in this case, if the radius of the circle is, I don't know, 5 meters, then that means the extension is 5 meters. Okay, but what if we had a spring with a natural length of 1 meter that was moving in a circle of radius 5 meters? In that case, X and R are different things. Okay, so even though the radius of the circle is 5 meters, because it has a natural length of 1 meter, the X value you would choose would only be 4. Okay, so there's a problem in the homework. I'm warning you right now. There's a problem in the homework where it's very similar to this, only the natural length of the spring is not 0. So there will be a difference between X and R. But in this case, because it has a natural length of 0, I can just do this. Okay. And so now I can plug in numbers. So I have, that's K times R. Okay, so I have 140 times R. We're trying to solve for R, so I leave it as a variable. Equals 4 times 11 squared over R. So this is a simple equation for R. I multiply both sides by R. I divide both sides by 140, and I get R squared equals 4 times 11 squared over 140. So then I take the square root of that, and I get that R equals 1.86 meters. So that's how that works. All right. Any questions? What? That's funny. I just imagined that I was in physical in-person class and I asked, "Are there any questions?" Just a knee-jerk response. Okay. So we'll do one more example with a horizontal circle. So I would also consider if you have something that's happening in outer space. Oh, now I remember which one I want to do. Okay. So let's suppose that a bicyclist of mass 50 kilograms goes in a flat circle of radius 12 meters. The coefficient of static friction between tire and ground is 0.8. Calculate the maximum speed. Okay, because okay, so first of all, let's break this down. We have a bicyclist who's riding in a circle. Okay. We have a bicyclist who's riding in a circle. And if you're on a bike, you actually want static friction to be acting between your tire and the ground. okay? Even though the bike is moving, it's actually static friction. Because think about that. Is your tire actually sliding against the ground? No, it is not, right? It's rolling across the ground. So rolling is different from sliding, okay? When you're rolling, the rubber in your tire isn't scraping against the pavement, okay? So even though you're moving, it's static friction, okay? Type it into the chat if you know what. If you have a car where kinetic friction is operating, what is the car doing? Okay, type it in if you know. All right, so it is static friction, okay? And as we know, the static friction, okay, so someone typed in drifting. Yeah, so peeling out, if you've ever seen a car peel out, the wheels are spinning, and hydroplaning would be kinetic friction as well. But anytime the wheels are spinning, and they're actually scraping across the pavement, that's when you have kinetic friction. Okay. So, anyways, we're going to start off with Newton's second law. And again, because I'm trying to calculate the maximum speed, okay, I'm going to use the v squared over r version of, okay. Now the centripetal force is static friction, okay. Now we had better the required static friction had better be less than the maximum value of static friction. So we had better have that static friction max is less than or equal to mv squared over r. Okay? Because we could think about mv squared over r is the force required to go in that circle. Okay? It's the force required to go in a circle with this radius and this speed. So if the actual force is less than this amount, then that means that you're going to fall out of the circle, okay? So we had better have that this inequality is true. Now the formula for maximum static friction is mu sub s times normal. Now because it is a flat circle, when you have a box that's just sitting on a flat surface, okay, if you have a box that's just sitting on a flat surface, the normal force is equal to mg. So static friction max is m times g. Or sorry, normal force is m times g. We can see that the masses cancel out. And I can actually solve this, and I get that the velocity has to be less than square root of mu sub s times g times r. Okay. So I like this because it makes a lot of sense. The bigger the coefficient of static friction, the faster you can go. All right. The bigger the radius of the circle, the faster you can go. In fact, going in a straight line, you can think about going in a straight line as moving in a circle of radius infinity. Okay. So you can see going in a straight line, you're not in any danger of peeling out, of skidding. So you can go as fast as you want in a straight line. All right, so plugging in numbers, we get square root of 0.8 times 10 times 12, which is the radius. Notice how the mass canceled out. So the mass of the bicyclist did not matter. So we have 0.8 times 10 times 12. is 96, square root of that. And we get about, the velocity has to be less than about 9.8 meters per second. So if you went greater than that, the bike is going to skid. You're probably going to fall. All right? So these are some examples of horizontal circle problems. Notice how we have to choose which force is playing the role of the centripetal force. Okay? In the case of a spring whirling you in a circle, it was the elastic force. In the case of a bicyclist, it was static friction. So there's all kinds of different scenarios. All right. So now what I would like to do is I would like to talk about vertical circles. Okay. Vertical circles. So vertical circles will have gravity as a centripetal force. Okay? And here's the reason why it is trickier. Okay? So if you think about moving in a vertical circle, okay, when you're at the bottom of the circle, gravity points down. Okay? So gravity actually points away from the center of the circle. So we would say that's a centrifugal force. Centripetal means in towards the center. Centrifugal means away from the center. Okay? If you think about being at this point in the circle, gravity points down. If you think about being at this point in the circle, gravity points down. If you think about being at this point in the circle, gravity points down. So you can see that it's like I drew a dream catcher. No matter where you are in the circle, gravity always points downward. So in these horizontal circle problems, the force was always pointed towards the center of the circle. Okay? In a vertical circle, gravity is changing directions relative to the circle, so that makes it more complicated. Okay, so I'm going to write out the master equations in a number of different scenarios, okay? Actually, 3 different scenarios. What if you're at the bottom of a circle? So we have, for example, like a car. Okay? And the car is going this way. It's at the bottom of a circle. This would be like if you went down a hill and you were at the bottom of the hill. Okay? If we think about it, the center of the circle is up here. So the direction of my centripetal acceleration is upward. Okay? This is kind of confusing because even though we think about gravity as pulling us downward, so the acceleration is downward. If you're at the bottom of a hill and you're moving, or in a ravine, your acceleration is actually upward because you're rising up out of the ravine. Okay, so what forces are acting on this car at this moment? We have the weight force is going downward. So we have mg going downward. And we have the normal force from the bottom of the ravine going upward, or the reaction force, or whatever. Okay? Actually, I should have drawn this arrow longer because the acceleration is upward towards the center of the circle. Okay? All right? So that means that there has to be more upward force than downward force. So let's go to So for all of these scenarios, we're going to use net force equals ma. All right? So what do we have for this first scenario? Well, the net force is up forces minus down forces. So it's going to be normal force, which is upward, minus mg, which is downward. And that equals mass times acceleration. The acceleration is upward. So it's going to be plus v squared over r. Okay, so that is the master equation in this scenario. So the trickiest part is getting the signs of each of these terms correct. Here the acceleration is upward, the normal force is upward, the weight force is downward. So the one with the negative sign is the downward thing, okay? Alternatively, what if the car was at the top of a circle with a certain speed? Okay. Here, if you're at the top of the circle, the center of the circle is down here. So we have a downward centripetal acceleration. Okay, that's a downward centripetal acceleration. We still have normal force going up. We still have weight force going down. In this case, the weight force had better be bigger than the normal force. Okay, because the acceleration is downward. So we've got to have the weight force bigger than the normal force in order to have a net downward force. So again, up forces minus down forces. So that would be normal force minus mg equals mass times the acceleration. But when I put in the acceleration, because the acceleration is downward, now it's going to be minus v squared over r. And keep in mind, this is multiplication. This isn't m minus v squared over r. It's m times the quantity negative v squared over r. Okay? And that's because the acceleration is now downward. So the trickiest part about this type of problem is that you got to keep track of the directions really carefully. Okay? One of the things that's interesting about this, has anyone, I'm sure you guys have driven through the bottom of a ravine, if maybe you're driving over some rolling hills. And one of the things you'll notice is that when you're at the bottom of the hill, you actually feel pushed into your seat by more than your own weight, okay? We can see why that is. The force that you're feeling of the chair on your butt is the normal force, okay? So we can see that if you're at the bottom of a hill, normal force is going to be mg plus mv squared over r, okay? So we can see that it's your weight plus something. So you feel more than your normal force is greater than your weight when you're at the bottom of a hill, okay? When you're at the top of a hill, all right, when you're at the top of a hill, rearranging this equation, you have normal force equals mg minus mv squared over r. So what we can see in this case is that the normal force is going to be less than the weight when you're going over the top of the hill. This is why when you're in a car and you're going really fast over the top of a hill, you feel kind of floaty. You don't feel that same normal force, and that makes you feel kind of insecure, floaty. Okay? There's a third scenario that I want to talk about, which is what if you were doing something like a skateboarder? Okay, you can imagine a skateboarder doing a loop-de-loop. So a skateboarder doing a loop-de-loop, the floor is actually above the skateboarder. Okay, so here's the skateboarder right here. Skateboarder is doing a loop-de-loop. Okay, now what's different about this one? In both of these examples, the floor is below the person, so the normal force points upward. Here, the normal force, or the floor, is above the person, so the normal force actually points downward. Okay? Gravity also points downward. The center of the circle is down here, so the acceleration is also downward. I'm drawing acceleration off to the side because I don't want you to think that the acceleration is a force, okay? So I'm putting it off to the side with a big goofy arrow. These arrows are for free body diagrams. So what do I get from Newton's second law in this case? Well, the normal force is down and the weight force is down. So I have minus F sub n minus mg. Okay, that's the net force. They're both negative. Equals, the acceleration is downward as well, so I have m times minus v squared over r. So in this one, all three terms are negative. All right, so in all three of these scenarios, we have three things to play around with. We've got normal force, weight force, and acceleration. And each of those could have different signs depending on the directions. Okay, so the key idea here is you need to get the directions of these forces correct. All right, so let's do two examples of vertical circle problems. Okay, so first example, a 50-kilogram human is in a car traveling at, I'm going to do my other example over here. A 50-kilogram human is in a car traveling at 30 meters per second at the bottom of a ravine of radius, let's say 20 meters. What is the normal force on the human? Okay, so I gave you sort of three scenarios right here, and it's a car at the bottom of a ravine, so it's this scenario. Okay, so I can see that my master equation is going to be normal force minus mg equals m times v squared over r. So it's the plus sign on mv squared over r. Plugging in the numbers, I have normal force minus 500 equals 50 times 30 squared over 20. Okay, so I will solve this for the normal force. And the normal force would be 2,750 newtons. Now this is kind of interesting, because if we think about what would be the normal force on a 50 kilogram human who was just standing on flat ground. In that case, that would be a scenario where normal force is equal to the weight. The weight of this person is 500 newtons. So because this human is moving in a circle, they're at the bottom of a ravine that's going in a circle, they actually experience more than 5 times the usual normal force. So this is why if you go, if you are in a roller coaster, for example, and you swing down into a dip, you feel pushed by your seat, okay? What that squished feeling that you're experiencing is the normal force increasing as a result of the motion that you're undergoing, okay? What if we have a car travels over the top of a hill? Of radius 20 meters. Okay. What is the maximum speed? The car can have without losing contact. So it's a car traveling over the top of a hill. So it's this kind of a scenario, okay? Now, you could imagine, if you watch movies, sometimes you have a car that's going really fast over the top of a hill, and they're going so fast that they actually leave the hill, and they kind of do like a little jump thing. So that's what we're asking is what is the speed such that if you go faster than that speed, you will actually lose contact with the hill and do like a jump, okay? So because we're going over the top of a hill, we're going to use this master equation right here, okay? So I move the minus sign to the front. Now here's the thing. Losing contact, you might recall that the normal force is the force of contact. So if you lose contact, you no longer have a normal force. So this is a key thing that you need to know, okay? Losing contact is code for the normal force becomes 0. Okay? Losing contact is code for the normal force becoming 0. So make sure you know that. So I'm going to go to the next line, and I'm going to not worry about the normal force. Okay, so I just have minus mg equals minus mv squared over r. So some of you might have been freaking out. You might have been like, the mass, I didn't give the mass of the car. And I can see that because the normal force went away, I now have two terms, both of which have mass, and so the mass cancels out. Furthermore, I can also see that the minus signs cancel out. So I just have g equals v squared over r. Okay. Gravity is 10, the r is 20, and I can solve that very easily for the speed. It's going to be square root of 200. So what I get is that the maximum speed is 14.1 meters per second. So if the car is driving at 20 meters per second and it goes over the top of this hill, it's going to actually go flying through the air. Okay? If the car is traveling at 13 meters per second, it's not going to lose contact, and it'll actually stay on the hill. All right? So that is my lesson for today. And I will see you in the Zoom room. Bye for now.